Right. Well, I'm apparently online, allegedly. Starting the stream. Just wave if you can see me. Cool. Well. Well then. Let me... Yellow. Right, how we doing? He's it Ganin? My faithful friends. Cool. Okay, so I'm not gonna go over pseudocode again because I think we spent a long time explaining that on the last stream, and I think you guys probably got it now. So yeah, there's likely to be some pseudocode that will appear in this next test. Some you might have to write some pseudocode. You will probably have to read some pseudocode, but it's all good. Everything's fine. Okay, so logic gates. Now in the hang on, if I just bring up the flippity floop, let me open up the thing. Scroll down to the bits about computational logic. Where is the thing about computational logic? Here we go. Right, let me just boom this up on your thing. Right, boom. Okay. Obviously, if you're not watching in 1080p, you're probably not going to be able to read this text. If you are watching in 1080p, then you've probably got a pretty good internet connection, so yay. Let's have a look, see what it says. Computational logic. Learners should have studied the following. Why data is represented in computer systems in binary form? Well, I'm pretty sure I've mentioned this a number of times, and you guys are usually pretty hot on answering. Can one of you that's watching at the moment, I think maybe it's only Blessed and Gabe who are actually watching right now. Can one of you say why data is represented in computer systems in binary form? Look at this Power Rangers mug. Mighty Morphin Power Rangers. It's filled with coffee at the moment. Power Rangers never drank coffee. Go Power Rangers. None of you answering the question. All right, well I'm gonna tell you, because it only understands ons and offs, ones and zeros. Yes, and the reason, let's be more specific here, the reason it only understands on and off is because it works on a bunch of electronic switches called transistors. The transistors are either on or they are off, which allows the electricity to flow through the different circuits which are arranged in special ways, and they are called logic circuits. So the whole thing, it's a bunch of on and off switches. Good. Simple logic diagrams using the operations and, or, and not. So if you are stressed out about things like XOR gates and NOR and NAND and what all of that lot, you don't have to worry, okay? And, or, and not. There's 3 gates that you need to remember. That's it. And I'm going to go through a whole bunch of them with you and point you in the direction of a wonderful website which I made. In fact, you could probably go there right now. binary.666.co.uk. There is a link to it in the chat right now. If you go there, I will show you what it looks like. Copy link location. It looks something like this. Okay, this is something that I knocked up to help people out with their logic gates. You cannot select like the checkboxes on the outputs. You can turn the inputs on and off. So the only 3 gates that you need to know about are these 3 gates at the top. Okay, so the AND gate is the one with the flat base and the round edge. The OR gate is the pointy one, and the NOT gate is the one with only one input. Okay, so AND gate, you will notice with both of the inputs off, the output is off. If I turn one of the inputs on, the output remains off. If I turn the other input on, the output remains off. If we have them both on, then the output is on. Okay. Greetings. GCSE pods say we need XOR as well. Well, the spec says that you don't need XOR, but I can briefly go over XOR. XOR is very simple. If you understand OR gates, you'll understand XOR gates. So an OR gate, if I turn one of the inputs on, doesn't matter which input it is I turn on, the output will be on. And if they are both on, the output is on. Now the difference between an OR gate and an XOR gate is that if you look down here, I've got my XOR gate. If both of the inputs on an XOR gate are on, the output is off. Okay? So if I was to write out the truth tables for these things, you may have to write out truth tables. If I'm doing truth table for an AND gate, A and B and output Q, if we have both of them off, the output is going to be off. If I have one of them on, output is going to be off. If I have the other one on, the output is going to be off. And if I have them both on, the output is going to be on. If I did the same thing for an OR gate, okay, the OR gate is, if they are both off, then it is off. Otherwise, they are all on. That's what the AND gate looks like there. I'll just reduce the font size so you can see 2 truth tables on one thing. So the AND gate, this one at the top here, you can see if they are both on, the output is on. That corresponds to this. Can I get my cursor over it? No, I can't. It's the way I've got my screen set up. So look at the this line here. Okay. If I move down to the OR gate here, you can see if they are both off, that's the only point where they are off. The XOR gate, okay, it's exactly the same as an OR gate with one slight difference. XOR. Okay, the only difference is if both of the inputs are on in an XOR gate, the output is off. Okay, the X is short for exclusive. Okay, so that's the difference. So the spec says you don't need to know XOR and or not. That's what it says. Okay, but there it is. This website, you know, you can play around with it. There's a little game at the end if you fancy a challenge, so you can have a play around with that. Things to remember: a NOT gate. The output is on if the input is off, and the output is off if the input is on. Okay, so a 1 is the same as true, as the same as on. Yes, 1, on, and true, they are all the same. 0, off, and false, they are all the same. Okay, in the exam, you're probably going to be asked for noughts and ones, but T and F might crop up as well. On and off is rare, but you know, it's still a thing. You just like, I mean, it makes sense, right? If you turn something on, then 1 is something. Yeah. If you turn something off, then it's nothing, and that's 0. Okay. So let's just quickly go back to the things here. Simple logic diagrams using the operations and, or, and not. Okay. So you guys may be aware of this website here. Logic logic.ly. There's a free trial. Let's try logically in the browser and hope that it works. I haven't actually tested this at home. There we go, it works. So if you I'll put the link in the chat there. This website allows you to experiment with different logic gates and see what happens. Right, the way that it works, you have your toggle switches which you can drag onto the thing. Can I zoom in on this? Is there a zoom function? Oh, there we go. Right, no, that just zooms the whole web page. I didn't really want to do that. Oh, there we go. Right. Okay, so here's my two inputs there. And if I put an AND gate on there and I get my little light bulb output, I can connect these up, and there you go. You can test these out yourself. And the great thing about Logically is it will show you which parts of your circuit are on. So you can see, and it means that if you were to set up a logic circuit like not A and B, there's A and B, and we are making it not that. You can see, now that's already wrong. I've messed up here. You know what? I'm just going to wipe this and start again. Right, so here's my switch, here's my other switch, here's my AND gate, and here's my not gate there. Okay, connect all of these up. Bing, bang, bada boom, pow. Okay, so there it is. If it says, oops, your web browser isn't capable of running this content, what are you using? Internet Explorer or something? Get a proper browser. You can download Firefox for free. That's the one I would recommend. You can get Chrome for free as well. You've got absolutely no excuse. Get a different browser. Okay. Right, so you can see here, because there is a 0 going into the NOT gate, the output is going to be 1, which turns the light on. As soon as I turn both of these switches on, the light goes off. Now, it's worth noting that this circuit that I have just created is this. It is not A and B. Okay, now there is some more terminology which I'll get into shortly. Okay. I've got Chrome, I just don't use it. You use Internet Explorer instead. That's like saying, oh yeah, I've got a Ferrari, you know, but my like 3-wheel trike is better. You know, what on earth? Anyway, not A and B. Now let's be careful, because that is not the same as not A and B. Okay? You see the difference here? Just like in maths, you do the brackets first. Okay? So not A and B is not the same as not A and B, because that not A, that happens before we feed it into the AND, so that would look like this. Okay, if we assume in this top one is A and the bottom one is B, we would have something that looks like this. Okay, and so you can see the circuit layout is different for these two circuits. This top one is not A and B. Okay, and the bottom one is not A and B. Okay, so two different circuits, but they look the same. Okay? So if you can see as well, I've got both of my switches on here, and the light is off. If I turn both of my switches on here, the light still remains off. Okay, but you may find that there are some slight differences. If I turn them all off, you'll notice that the light is on this one and it's off on that one. Okay, so make sure that you get the order of these things correct. Okay, I mean it's pretty straightforward. I would recommend trying a few different things out. So let me just go back to the binary logic gates thing here. You'll notice it says Year 9 computing. I'm introducing it earlier on for people. I'm guessing you know the concept of truth tables because I just went through it. It's an example of a compound logic circuit. Okay, have a look at that logic circuit. Someone tell me what the how you would write that logic circuit. Would we have to draw truth tables combining logic gates? Perhaps, yes. They would not be very complex. Maximum 2, unlikely to have more than 2 gates. And certainly they would not be anything more complex than... right, you can't just write and. You've got to have it in reference to some of the inputs. Yes, they are 2 AND gates, but you need to say how the inputs go. Okay, so think about these first 2. Okay, the A and the B are both feeding into this AND gate, and then the output of that is feeding into another AND gate with C. Is that C and C and A and a smiley face with sunglasses on? That's converted to an emoji. C and put a space, put some more spaces in before the bracket. It should be A and B and C. Okay. Now the precedence of AND means that you don't actually need those brackets in there. You can just say A and B and C. Okay. It's the same thing. Okay. Because if you look here, we've got A and B here, and that is ANDed with C. Okay, so it's the same as saying C and A and B. It's the same thing, you know. But you know, it usually helps to write out in terms of the letters as they go along. So A and B and C. You know, my eyes hurting at the moment. I've had it's been a rough weekend. What have I got here? There's another example. Oh, that's the example in Logically there. So this is a much more complex circuit, and there's some joy. Sarah's not been hitting a joint. I don't even drink, let alone do drugs. So that's you will not find me on the other end of anything nefarious like that. Let me just pull up the other lesson that I had here. Some more advanced stuff in here, because there's some other stuff that you need to know. I hope you painted the entire house black and then drew pentagrams on the wall. That's what I'd do to my grandparents. Well, I would do, but they're dead. So anyway, right, there are some symbols that you need to know. Okay, obviously up until now I have been writing A and B, or I've been writing not or. Okay, but you need to know these symbols, right? So AND is this upside down V thing. Okay, or is kind of like a V, okay, and not is that symbol to the left of 1, which you never knew what it was. If you press Shift and the key to the left of 1, there you go. Okay, so and, or, and not. Now, a way of remembering that, and looks like the letter A that hasn't properly been, like, you know, filled in. Okay, V is like if you imagine a football team playing another football team, one or the other is going to win. Aston Villa v Man United, yeah, that's one way of remembering it. And then not is the other symbol that isn't either of those. Simple, right? So if I was to write something like this, can someone tell me what this would represent? What would that represent? Not A or B and C. Yes, bang on. You got it. Okay. Now, in the exam, they are very likely to present these symbols. Okay. So you've got to make sure that you know them. If you do not know them, write them down. Okay, memorize them. And, or, not. You can make a song. And, or, and not. Don't ask me. I don't know. It's been a long day. I did have a little worksheet here. Let's have a look and see what we've got here. So, let's do this one here. Okay, I will copy and I will paste it into here for your delectation. So we've got that. First of all, can someone tell me what circuit that represents? This circuit here. Can anyone tell me what it represents? A and B, or C and not D. Excellent. So I am going to draw it here on thingamawhatsit, logically. If you want, you can try drawing it at home using logically and see if yours matches what I've got here. Okay, so we are going to need an input for each of the letters. I am going to label these inputs as well. So that one is going to be oops, didn't mean to do that. That's going to be A, and then we are going to have a B, and we're going to have a C, and we're going to have a D. A, B, C, D. Okay? So first of all, A and B. Okay, remember, stuff that's in brackets happens first. So we've got to work out A and B, and then we've got to work out C and not D. Okay, so we'll start off with A and B. That right there is A and B. Simple. Okay, so let's do C and not D. Well, to get not D, we're going to need a not gate in there. We're also going to need an AND gate, so we're going to have C and not D. Okay, so we've got A and B here. We've got C and not D here. Okay, and we have the an OR gate. Both of those are going through an OR gate together. Okay, so there's my OR gate. Join it up. Boom, and finally the output. And there is our circuit. A and B, or C and not D. Okay? On the 666 thing, I think it's Cairo, but I'm not sure. What? Don't know what that means. Oh, you mean on the Enlightenment thing? I don't know what level you're on. Anyway, that's by the by. Okay, so yeah, I mean, I don't really know what else there is to say on logic gates. You've got AND gates, you've got OR gates, you've got NOT gates. Okay. Incidentally, you can build an XOR gate using if we have, let's get rid of half of this stuff. Boom. Okay, I'm going to get rid of these labels. So an XOR gate is like saying A and not B. A and not B, or not B and A. Okay, so we have A and not B, or let's get some more shenanigans going on here, B and not A. Just arrange them so that it's nicer to look at. Okay, so you can see if one of them is on, the light bulb is on. If they're both on, it's off. If they are both off, it is off. Okay, that is how you build an XOR gate using nothing but AND, OR, and NOT. Okay, so yeah, that's that. It's worth noting you can build literally any logic gate out of a combination of NAND gates, but that is beyond the scope of the GCSE, so you don't need to know about it. Does anyone have any other questions about logic gates? So we've covered why data is represented in computer systems in binary form. We have looked at simple logic diagrams using the operations AND, OR, and NOT. We've looked at truth tables. We have looked at combining Boolean operators using AND, OR, and NOT to 2 levels. So it's like I said, you're not going to be asked to combine more than 2 gates in a row. Okay. Applying logical operators in appropriate truth tables to solve problems. I'm not entirely sure what they mean by that, but I'm guessing that that is creating truth tables from compound logic gates. So yeah, applying computing related mathematics. Plus, minus, divide, times, exponentiation, and as I mentioned before, they use this symbol for exponentiation. Confusingly, it's the same as the AND symbol, whereas in Python we would use that. So if you see something that says 3 raised to the power of 5, you know, that's like 3 times 3 times 3, 3 times 3 times 3 times 3 times 3. There we go, 3 to the power of 5. Okay, and then mod and div. So can you remember what mod and div were? Can anyone say? First of all, let's say mod. What is another way of saying mod? A maths concept that you should all be familiar with from your days in primary school. What is mod? Modulus, yes. Well, there's another word. A more commonly used word. Not times. Begins with R. Not range. Remainder. There we go. The modulus is the remainder. If I say 12 mod 5, okay, that's how many times can 5 go into 12, right? It's not that, it's what is remaining after we have divided 5 into 12, however many times it goes. Yeah, 12 mod 5 is 2, because 12 divided by 5 is 2, remainder 2. Okay, so what about div? What's div? Clues in the name. It's similar to mod, but not quite the same. It is division, but it's a special kind of division. Yes, it's integer division. Okay, so it's how many times that number can divide into the other number, and ignoring any remainder, ignoring any decimal point. Okay, there's no decimals, it's just whole numbers, integers. Okay, so those sorts of things will likely crop up in any thingamabobbamadudars. The what's it called? What are they called? Algorithms. That's right, algorithms. Cool. And that's all the stuff you need to know on computational logic. Pretty simple. I mean, most of it, you know, in terms of like how it's applied, it's just using and, or, and not in in algorithms and stuff like that. But you know how that works. So let's just go through and have a look at this. So learners should have studied the following: computational thinking, abstraction. Do you know what abstraction means? Yes or no? Okay, abstraction, right? Let's see. How should I word this? Imagine that you are creating a simulation of your bedroom. Okay, you want it to be pretty realistic, right? So you want to get all of the furniture that's in there. You want to make sure that the walls are the right color and stuff like that. Now you could go around your entire house and you could like find out what the colours of the walls are downstairs. You could go next door and find out what the colours of their walls are, but you don't need to. Okay? In order to create your accurate model, you don't need that kind of information. It's like, yes, you could build the rest of the house and that would make it super realistic, but if the whole point of what you're doing is to simulate your bedroom, you don't need the rest of it. Okay? Abstraction is when you just take what's actually necessary for constructing some sort of computerized model. I've got an example for you. An example you've probably seen a million times before without realizing it. Okay? What have we got here? What is the name of this thing? What is the name of this thing? It's a map. Okay, now, does the real world look like this map? No, it does not. Okay, if I turn the satellite map on, okay, the real world, it kind of looks like this, okay, because this is actual satellite photography. But it makes it a little bit more difficult to read. And if we are like, you know, trying to find a road somewhere, I mean, it's pretty confusing what all of this stuff is, right? So what we do is we use an abstraction. Okay, we remove the information that's not necessary. Okay, we've got these roads. Like these roads, they're not actually bright orange like that, but it helps us to see what's going on. Yeah, we don't have the picture of the British Motor Museum here, but we've got a little label that says it's there. Okay, so the abstraction here, it's removing unnecessary details from a system so that you can make a a computerized model. Because the problem is that there's so many different variables. I mean, in order to properly accurately measure the weather, we would need to know what every single molecule of air on the planet was doing at any given time. And it's not possible for us to know all of that stuff. And even if it was, we would not have the computing power to process it. Okay, so there comes a point where we have to say, right, let's take the information that we've got, let's get rid of some of that other stuff because it's not really necessary. Okay, there may be times when using an abstraction can make things more difficult and less accurate. Okay. If I want to find my way home, and this is my map that I've got, it's like, well, that's great. I can see that Kazakhstan's over there, but that doesn't really help me out much. Okay, so when you use abstractions, sometimes you risk losing some fidelity, or you risk losing some accuracy. Okay. What would you say a definition of abstraction is? It's taking a complex real-world situation and modeling a simplified computerized version by removing unnecessary details. That's a definition of abstraction. Okay, but remember, this is the computer science definition of abstraction. Okay, that's the context that we're using it here. Yeah. You talk about abstraction in art, it's something completely different. You talk about abstraction in something else, it's completely different. You will not be asked to define abstraction. Okay? You may be asked to use abstraction, or you may be asked to identify where abstraction has been used in a given example, but you will not be asked to define it. Okay? Now then, where did we get up to? What else? Decomposition. Okay, decomposition. That is where you take a complex problem and you break it down into a number of smaller problems. And you take each of those smaller problems and you break them down into even smaller problems until you reach the point where you cannot break those problems down any further. Okay? You then solve those simple problems one by one, and then when combined together, they work to solve the entire problem. Okay, yes, so breaking something down until it is an atomic problem which you can just easily solve, it becomes trivial to solve. Okay, and one of the ways that modern computer languages help us is once we've decomposed the problem, we can use functions to solve those individual problems before joining it together as a whole. Okay, and algorithmic thinking. I mean, that's just being able to follow algorithms line by line, understanding where they jump to, function calls and things like that. Okay, so when it comes to computational thinking, they're not going to ask you questions. They're not going to say, hey, what's abstraction, or what's decomposition, or what's algorithmic thinking. They're not going to say that. What they are going to do is they are going to give you questions that require you to use those skills. Okay? They will give you a complex problem which you then have to break down into smaller problems. Okay? They will give you sometimes they might give you a picture of a map and they will say, how has abstraction been used in this? And you say, well, you know, they've removed unnecessary details, blah, 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 blah. Okay? And the algorithmic thinking that comes into these other sections here. Standard searching algorithms, binary search and linear search. We covered them in extensive detail. And bubble sort, merge sort, and insertion sort, we covered all of those as well. How to produce algorithms using pseudocode, using flowcharts, interpret correct or complete algorithms. Okay, so one of the things that they're quite hot on is they will give you an algorithm which doesn't work, or an algorithm which is slightly incomplete, and they will ask you to finish it off. So do sorts I forgot. Right, I don't have time to go through every single sort, but I can give you a quick example. So let's go to the. I'll tell you what. I'll do a quick sort down here. Not a quick sort, because you don't need to know the quick sort until A level, but I'll do a I do a series of sorts. Let's say I have this list. In fact, can I... Maybe I can go to paste bin and type some stuff in so that you can see it a bit better. Is that gonna work? Maybe. You see that all right? Is that text okay? Zoom in a little bit more. Boom, boom, boom. Okay, I understand. Right, okay, so let's say I've got some numbers 4, 3, 7, 6, 2, 8 and 1. That is my list that I'm going to sort. Okay? So the easiest sort is probably the insertion sort. Okay? This is where you end up sort of partitioning the list into the sorted section and the unsorted section. Okay, so to start off with, we assume that the first character is the sorted section of the list, and then we have these are the numbers 3, 7, 6, 2, 8 and 1. Okay, the next thing we do is we look at the next number, okay, and we find its position in the sorted list. Okay, so we take this number 3 and we slot it in the position in the sorted list where it belongs. Okay, 3 is less than 4, so we know it's got to go before there. So the next position that we end up with is 3, 4, and that's our sorted portion of the list. 7, 6, 2, 8, 1. Okay, same thing again. 7. Okay, well 7's greater than 4, so that's just going to sit in the same place there. So we end up with 3, 4, 7. And there's our sorted part. 6, 2, 8, 1. Okay, the next thing is 6. Okay, 6 is less than 7, so it's going to swap places with 7. It's greater than 4 though, so it's going to stay there. Okay, so we end up with 3, 4, 6, 7. There's our sorted portion. 2, 8, 1. Okay, and then 2. Well, 2 is less than 7. So it's going to swap places there. It's less than 6, so it's going to swap places there. It's less than 4, so it's going to swap places there. It's less than 3, so it's going to swap places there. So we end up with 2, 3, 4, 6, 7. You can see how this is gradually getting sorted. The closer we get to the end is 8 and a 1. Okay, and then 8. Well, 8 is greater than 7, so it's going to stay where it is. So we end up with 2, 3, 4, 6, 7, 8. And there's 1. Okay, and then finally that 1, well, it's less than 8, so it's going to swap. It's less than 7, so it's going to swap. It's less than 6, so it's going to swap. It's less than 4, so it's going to swap. It's less than 3, it's going to swap, and it's less than 2, so it's going to swap there. And then we end up with 1, 2, 3, 4, 6, 7, 8, and there's our sorted list. Okay, that is the insertion sort. Okay, the insertion sort. I would highly recommend that you go back to the stuff on the Google Classroom, because on the exercises that I set, there's full instructions on these sorts. So if I just blank the insertion sort now, let's have a look at the bubble sort. Okay, so the way the bubble sort works, we look at the first 2 items in the list. If the first item is greater than the second one, we swap them over. If we make any swaps, we make a note of it. Okay, so we swap over those 2. We end up 3, 4, and then 7, 6, 2, 8, 1. Okay, we made a swap. Okay, and then we're looking at the next 2, 4 and 7. Well, they don't need to swap, so we just move on to the next 2. 7 and 6, they need to swap, so we swap them over. So we end up with 3, 4, 6, 7, 2, 8, 1, and doesn't matter that we made a swap that time, so we made a swap last time. Okay, so we know we've made at least 1 swap here. So now which ones are we looking at? 7 and a 2, well, they need to swap over as well, so we're going to swap them. Okay, so we end up with 3, 4, 6, 2, 7, 8, 1. We made a swap. Okay, next up we've got the 7 and an 8. They don't need to swap. 8 and a 1, they do need to swap. Okay, so we end up with 3, 4, 6, 2, 7, 1, 8, and swap. Now we've reached the end of the list. Okay, we know it is not sorted because we have made a swap. If you make at least one swap, you know the list is not sorted. Okay, so that's the end of our first pass. Okay, end of pass 1. Okay, so now we start a whole new pass. So we've got 3 and 4, they don't need to swap. 4 and 6, they do need to swap. No, they don't need to swap. 6 and 2, those are the ones that need to swap. So we end up with 3, 4, 2, 6, 7, 1, 8, and we made a swap. Okay, so next up we're looking at 6 and 7. They don't need to swap. 1 and 7, they do need to swap. So we end up with 3, 4, 2, 6, 1, 7, 8, and we made a swap. Okay. The last one was called Insertion Sort. This one is called Bubble Sort. Okay, so where do we get up to? We just swapped the 1 and the 7. 7 and 8 don't need to swap. Okay, so this is the end of pass 2. We made at least one swap, so we know it's still not sorted, so we've got to go back and start again. 3 and 4 don't need to swap. 4 and 2 do need to swap, so we end up with 3, 2, 4, 6, 1, 7, 8. We made a swap. So now we are looking at 4 and 6. They don't need to swap. 6 and 1 do need to swap. So we end up with 3, 2, 4, 1, 6, 7, 8. And we made a swap. 6 and 7 don't need to swap. 7 and 8 don't need to swap. That is the end of pass 3. Okay, we made a swap. So we have to go back and start all over again. 3 and 2 do need to swap. Okay, so we swap them first of all. So we swap 2, 3, and then we've got 4, 1, 6, 7, 8. We made a swap. Next up, 3 and 4 don't need to swap. 4 and 1 do need to swap. So we end up going 2, 3, 1, 4, 6, 7, 8. We made a swap. What is next? 4 and 6 don't need to swap. 6 and 7 don't need to swap. 7 and 8 don't need to swap. That is the end of pass 4. We made at least one swap, so we're still not done yet. You see how inefficient the bubble sort is? Okay, so we end up don't have to swap 2 and 3. We do have to swap 3 and 1. Okay, so 2, 1, 3, 4, 6, 7, 8. We made a swap. Next up, 3 and 4 we don't need to swap. 4 and 6 we don't need to swap. 7 and 8 we don't need to swap. So that is the end of pass 5. Next up, 1 and 2 need to swap. So 1, 2, 3, 4, 6, 7, 8. Okay, we made a swap. Let's have a look. 2 and 3 don't need to swap. 3 and 4 don't need to swap. 4 and 6 don't need to swap. 6 and 7 don't need to swap. 7 and 8 don't need to swap. This is the end of pass 6, right? But we made a swap. Even though I can look at that list, I can see that it is sorted, right? We made a swap, so we have to go through again. Okay, so let's have a look. 1 and 2 don't need to swap. 2 and 3 don't need to swap. 3 and 4 don't need to swap. 4 and 6 don't need to swap. 7 and 8 don't need to swap. So we can copy out our list. We made no swaps. Okay, so that's the end of pass 7, and the list is sorted. Okay? That's long-winded. That's the bubble sort. The bubble sort is rubbish. Okay? Will be questioned on search algorithms. Yes, you will. Okay. The other sorting algorithm is the merge sort. Okay. The merge sort is the fastest of the three that you need to know. It also requires the most memory, and it's probably the most difficult to get your head round. Okay, so let's have a look at this. We start off by splitting our list of 7 items into 7 lists of 1 item. Okay, so we end up with a 4, 3, 7, 6, 2, help if I could type, 8, and 1. Okay, we now got all of these lists. We start by comparing the first 2 lists. We're looking at the first item in each list. Because each list only has a single item in it, that means we're just looking at the items in either list. Okay, we are going to merge them together to form a list of 2 items. Okay, so we start off by moving down the lowest of the items. So that 3 goes down to there. Okay, that 3 is now gone. Okay, now we're comparing the lowest of the first items in the list. Well, this has no items, so it's got to be the 4 that moves down there. Okay, so we're done with those first 2 lists. We're now comparing these next 2 lists, and we are going to create another list containing 2 items, okay, from these 2, for merging them together. So we look at the first items in each list. 6 is the lowest, so we move it down here. Okay, 7 is the lowest out of this item and the item that doesn't exist, so we move that down there. There's our second list. We now compare these 2 lists. Okay, same deal. Okay, 2 is the lowest, so we move that down here. This is the merge sort, yes, and then we are going to move the 8 down here. Okay, now we're left with this one list on its own, so that just follows us down here. Okay, now we are going to merge these 2 lists. Okay, now this is the bit where you've got to be careful. Okay, you're always, every time, looking at the first item in each list. Okay, you don't care about what the other items are. You are moving the first item in each list. So the first item in this list is 3, the first item in this list is 6. 3 is the lowest of the 2, right? So we got to move that down here. Now this is the point where you've got to be careful, because the temptation is to say, oh, the 3 moved down there, now the 6 moves down there. But if you look, 6 is not the lowest of the first items in these lists. 4 is now the first item in this list, and that is lower than 6, so that gets moved down. Okay? And now we're still comparing the first items in this list. 6 is the first item in this list. There are no items in that list, so we know that 6 has to go down here. Okay, and the same deal with the 7 there. Okay, so that's just going to move down here. Okay, and that's our first list merged. Now we're going to merge these 2 lists. So we're comparing this first item in this list, which is 1, and the first item in this list, which is 2. So the 1 is going to move down here, and that's going to be followed by the 2 and then the 8. What's the glowy circle behind me? I don't know. What glowy circle? There's a... Where? What? Where is it? That thing. That there. That's my bike helmet. On the bookcase. Oh, it's a it's a karate trophy. Yeah, it's a karate trophy. Okay, so we're almost finished. We've just got 2 lists to merge. Same deal applies. We're looking at the first item in each list. Okay, we've got a 3 there, we've got a 1 there. So the 1 is going to move down here. Okay, we're now still comparing the first items in each list. There's a 3 there, there's a 2 there. The 2 is going to move down. There it is. We're now comparing the first items in each list. The 3 is the lowest, so that's going to move down there. The 4 is the lowest here, so that's going to move down. Okay, the 6 is the lowest there, so that's going to move down. And then the 7 is going to move down. And then the 8 is going to move down. Okay, and that's it, sorted. That is the merge sort. Okay? Those are the 3 sorts. Now you're probably thinking, oh, but what about searching algorithms? Okay, cool. Let's do a search algorithm. I'll still use these same things. Okay, we're going to start off with the linear search. Linear search is super duper simple. Let's say I want to find the index of the number 2 in this list. Okay, I check index 0. Is that 2? No, it's not. Move on to the next one. Is that 2? No, it's not. Okay, move on to index. Sorry, that was index 0. That was index 1. Move on to index 2. Is it 2? No. Move on to index 3. Is that 2? No. Move on to index 4. Is that 2? Yes. Therefore, 2 is at index 4. That's it. That's all there is to the linear search. You go through it item by item until you find the thing that you want. The downside of the linear search is if you are checking for something which doesn't exist in your list of items, you have to check the entire list before you find out that it's not actually in there. Okay. Now, if we were to do the binary search, binary search is an example of a divide and conquer algorithm because you are halving the search space every time you do it. How do you show that we've done it? Okay, so I'll just do a I guess check index 0, not found. Check index 2. Sorry, check index 1, not found. Check index 2, not found. Check index 3, not found. Check index 4, found. Index of 2 is 4. You know, that's it. That's all you can do, really. It's crap. You know. So, binary search. Okay, number one rule that most people forget with binary search. The list has to be sorted before you can search. Okay? If I had a penny for every time that someone has forgotten that the list has got to be like sorted before you can search it, I'd probably have, I don't know, about 15p or something. You know. Positives of the linear search is super simple to implement. It's really easy. And it's very fast for small lists. That's it. Yeah. So, if we're going to do the binary search, we've got to sort this list. We know that the sorted list is 1, 2, 3, 4, 6, 7, 8, right? There we go, that's sorted. Okay. Now, let's say, again, I am searching for the index of the number 2. Okay. There are a grand total of 1, 2, 3, 4, 5, 6, 7 items. Okay. The middle index is this one, 0, 1, 2, 3. 7 div 2 is 3. Yeah. There you go. Yeah, it's very slow for long lists. Also, if the other thing as well is if you are searching for something that doesn't exist in your list, you have to search through every single item before you find it. Okay, binary search is way more efficient. Okay, 7 div 2 equals, it's not 2, it's 3. 7 div 2 is 3. So we're going to start off with index 3. Okay, is index 3 the thing that we're looking for? No, it's not. Okay. The next question we ask is the thing we're looking for higher or lower than the thing at index 3? It's lower. Okay, if that's the case, then we ignore the top half of the list and we just search in the bottom half. Okay, so we're just concerned now with 1, 2, 3. Okay, so now our indices start at 0 and they end at 2. Okay, 2 div 2 is 1, so we're going to look at index 1. Okay, is index 1 the thing we're looking for? Yes. Index of 2 is 1. Okay, that's it. So remember, it's like that game. It's like that game where you say, I am thinking of a number between 1 and 100. You know, you guess 50 to give yourself the best chance of finding out. If they say, no, it's lower than that, then you would guess 25. Okay, you're selecting the midpoint of each of your sublists every time. Yeah, high-low. That's all it is. That's the binary search. Okay, that's why I use that game to introduce binary search in my lessons, because it's the same damn thing. It's the same thing. There you go. Cool. Do we have to show that we've ordered the list before we start? Well, yeah, because otherwise it ain't gonna work. I mean, it depends on the question. If they probably will not have a question where it's like, do this whole binary search thing and show literally every step of the way. Okay, but they might have a question saying, why will the binary search not work in this situation? Because the list ain't sorted. Yeah, something along those lines. All right. Now then. Okay, so I'm going to skip down now. We've been on for about an hour. It's probably not going to be as long as last live stream because, we shall see. Okay, let's have a look at this. Programming techniques: the use of variables, constants, operators, inputs, outputs, and assignments. I'm not going to teach you that because you damn well know that. You must know that. Okay? Variables. You know, like name equals Bob. Okay? In this example here, we have used an assignment as well. When you say this variable equals this value, you have assigned that value to the variable. Okay? Inputs. Name equals input. What is your name? Okay, when you're writing in pseudocode, you can write it like that. If you're writing in Python and you're asking for a number, remember to convert it to an integer or float. Outputs, print name. Okay. Someone tell me the difference between a variable and a constant. One does not change. Yeah, which one does not change? Yeah, the constant. Constant doesn't change. And convention is, if we have a constant which doesn't change, the convention is to write its name in block capitals, something like this. Okay? Boom. Yeah? Good. Sequence. That's a bunch of commands executed in order. That's all a sequence is. Selection. That's if statements. Iteration, count and condition controlled loops. Those are loops. Do we have to write constants out like that? It's a good habit to get into. Okay? Write them out in capital letters. I mean, that's in Python because there's no way of specifying a constant in Python. But in a strongly typed language like C++, for instance, you would have to do something like const int pi equals blah 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 3.1415. Okay, you'd have to specify there was a constant. And yeah, use capital letters for your constants. Right, what do we got here? Iteration, that's loops. A count-controlled loop is a for loop. Okay, so for I equals 1, 2, 5, do something. Next, I. That's an example of a for loop in pseudocode. For I in range 5, do something. And that's it, you don't have to end it, okay? That is a count-controlled iteration. A condition-controlled loop is a while loop. While input does not equal 1, input I'll say actually while I does not equal 1, input I, end while. Okay, there's a while loop in pseudocode. Okay, while I does not equal 1, I equals int input. It's not going to fit on one line. It's going to look a mess. There you go. That's the thing. I know it's trying to connect my phone to my laptop's hotspot, but it keeps saying on my phone network access denied. It sometimes your phone ISP will not allow you to access hotspots. Wait, you're trying to connect your phone to your laptop's hotspot. Well, then presumably. Are you using a router? Usually it would be the router that you would need to connect to. So yeah. Anyway, blah 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 blah. Use of basic string manipulation. You know, so that's like hello plus you. That's obviously going to write out hello, you, all together, you know, string concatenation and stuff like that. I've been through this 1,000 times and I went through it extensively in the last video, so if you want to recap that, go look at that. File handling operations, open, read, write and close. Again, we looked at that last time. The use of records to store data. The use of SQL to search for data. Have you covered SQL? Or SQL, as people that don't know how to pronounce it might say? Don't think so. Okay, so give you an idea of what SQL might look like. If I did something like select star from users where name equals Carl. Okay, it's for accessing databases. So this will pull out all of the records. Select star means, like, you know, sorry, all of the fields. So it's going to select every single field from the users table where the name field equals Carl. Okay, so that will pull out Carl Smith, Carl Pilkington, Karl Marx, all of those Carls that are in my imaginary database of people. If you don't know SQL, there really is not enough time for me to go over this. So if you get a SQL question, give it your best shot. And let me know, because obviously I will have to go over that. Other SQL commands: insert into users, name, age, values, Jim, 32. for instance. I mean, you can kind of guess what that's doing. Yeah, that's inserting. That should be lowercase. That's inserting the values into the users table. So it's accessing the users table. It's adding name and age. It's adding these two values, Jim and 32. Okay. So there's that. Drop table users deletes a table. You could also do delete from users where name equals Gabriel, for instance, and that would remove everything from the users table for people that are called Gabriel. Now, I don't think you need to know many more SQL commands than that. Select is the one that's used the most. But yeah, if you need extra help with SQL, then we'll spend some lessons on it. We've got time, I'm not expecting anyone to do super well on paper 2, I should say, because there's still stuff that we need to cover. Okay, so don't worry too much about the SQL, but there's some stuff. Use of arrays, both 1 and 2 dimensional arrays. I covered that last time. Functions and procedures, I'm pretty sure I covered that as well. Common arithmetic operators, that's your plus, minus, divide, multiply, all of that stuff. Common Boolean operators, and, or, and not. Okay. Now, this is the thing. Producing robust programs, defensive design considerations, input sanitization. When you sign up for a hey, someone give me a website that I can sign up for. And tell me a website I can sign up for. RuneScape.com. RuneScape.com. Let's go to RuneScape.com. Here we go. What do we got here? Play now? Is that where I create an account? I don't want to download it. How do I sign? There we go. Sign in stroke join. Create an account. Right, now this is interesting. Sign in with your email. I see a problem here. Let's say ka.smith@warriner.oxon.sch.uk. Password. Date of birth, that's a closely guarded secret. Let's say 23rd of April 1923. I don't want offers, I don't want to see relevant content. I am not a robot, I promise. When I click play now, let's see what happens. Now this is interesting. Jagex here have not used robust programming here. Because if I'd have spelt my email address wrong, something, I probably wouldn't have been able to log in. So here's the interesting thing. How do you think we could have made it a little bit better, so that I'd have thought better of Jagex, to be honest. How do you think we could have made that a little bit better, to make sure? I mean, I did spell my email address right, but if I spelt it wrong, how could we have avoided any potential shenanigans? Yeah, well, send me an email to verify my account, but if I spelt my email wrong, then if I spelt my email wrong, I'm not going to get that email, am I? Type email again, yes. Having a separate box where it's like, what's your email address? And then there's another box that says, no, seriously, what's your email address? Okay? You should never ever just copy and paste your email from one email box into the second email box. No, don't do that. Okay? By having that second, it's verification. It's to make sure that what you've typed in is correct. If you've typed it in, if I've typed this in like like it is here, and then I type it in again in a second box and I've spelled it differently, then we know that there's something up, right? So double entry can save problems later on. Okay. Input sanitization. I showed you the XKCD, right? Little bobby tables here. Let me just zoom in on that. There we go. You've got to make sure that you check, like especially on websites, you've got to make sure that you check to make sure that people can't execute code by typing into your text boxes. Okay. SQL injection, JavaScript injection, these are problems, and sometimes what people will do is they will type in like they will put a close quote marks in there, or they might type in some HTML which will close the tags and then allow you to execute some code and stuff like that. Generally speaking, when you are asking the users for input, you've got to make sure that you strip out any characters that could cause problems. Okay, that's what input sanitization is. It's making sure that the stuff that's been typed in can't be used to do nasty stuff. So you see here, there's some SQL that's been typed in. Robert has he's typed in his name and then closed a quote mark, closed a bracket, and put a semicolon, which would then effectively end that first SQL command and then execute another SQL command, drop table students, and then that's obviously caused problems. Input sanitation as well. Something as simple as like when you ask the user for their age, making sure that they only enter a number data. Okay. So there's a number of different things that you can do in order to make sure that what people are typing in actually makes sense. A lot of this stuff, if you don't know the answer because you haven't been taught it in the lesson, just think about your experience. You've done so much stuff online already. Think about some of the stuff that you had to do when you are signing up for stuff. Okay, anticipating misuse, that goes hand in hand with input sanitation. Sanitization even. Planning for contingencies and authentication. How many of you have a Origin account or an account that uses this wonderful little app? Okay. I don't know if you can see that. Probably not. You can see this is my authenticator. Is this a security risk? Maybe, but I don't think it's that much of a problem because you can't see what these things are for. But every, say, 30 seconds, those codes change, right? And so the idea is when you sign in, it will say open up your authenticator and type in the code that's in there. It's synced in with the thing. Okay, so the other thing as well, 2-point authentication. When I sign in on Steam, it will drop me an email saying, "Is this actually you that's signing in?" To make sure that that nastiness doesn't happen. I'd highly recommend setting up 2-point authentication if you haven't already. Don't think that you won't get hacked. My Origin account got hacked a while ago, and some Russians got it. I mean, I don't really play games on Origin, but there you go. But yeah, it was a hassle to get it back again. There you go. Right. I mean, we are running out of time rapidly. So let's let's see, what do we got? Testing. The purpose of testing. Why do we test computer programs? There's a question. Why do we test computer programs? To make sure they work is one thing. Yeah, to make sure they do what they are supposed to do. That's one reason. Yeah, so we can pick up on faults and errors. Yeah. To save the company's fame if something goes wrong. Yeah, unless that company's Bethesda, in which case, yeah, I wonder if they even tested Fallout 76. Stop security breaches. Yeah, I mean, obviously, it's all of these things and more. Okay, so we test the programs to make sure that they do what we want them to do. We also test them to make sure that they don't do what we don't want them to do, if that makes sense. When I was a games tester, one of the games that I was testing was Colin McRae Rally. So one of the things that I had to do was drive around the course, right on the edges of the tracks, making sure that you couldn't like bash through the walls and fall out of the planet. Driving backwards around the course, that's another thing that you have to test. You know, you have to test all of these things that you don't actually, you know, you think, well, that's not the intended use, so I don't have to test that. You've got to remember, people will do all kinds of crazy stuff that you hadn't anticipated. Okay, if you say to someone, type in your age, you know, someone is going to like mash the keys and try all sorts of stuff. Okay, so you've got to test absolutely every eventuality. You've got to test to make sure that the limits that you put on like name entry don't cause the users to be able to enter a massive name which fills up the entire screen. And top tip, by the way, W is the widest letter, so if you fill your text box with W's to make sure that it doesn't like spill off the outside of the page or break outside of windows and stuff like that, there's a key. How hard would you say it's to detect or find glitches and bugs? Depends on the game. Depends on the tester. I mean, it also depends on the state of the game. When you're testing in the early stages of the games, it'll be riddled with bugs, riddled with errors. Towards the last stages of the game, when it's like close to release, there'll still be plenty of bugs in there, but they won't be as serious. So you won't. It's very, very rare that you'll find a game that has a Class 1 bug in it. A Class 1 bug is something that causes the system to crash or the game to halt and prevent progress. It's also fairly rare to find Class 2s. Class 2s are severe bugs which affect gameplay, like your car exploding into polygons and stuff like that, or falling out of the environment and stuff like that. You'll probably find quite a lot of Class 3 bugs, like, you know, oh, there's one tiny little bit on the world where if you time it just right, you can get hit by a grenade and that'll send you into like some boxes from which you can't escape, you know. But then Class 4 bugs are sort of like, you know, that's sort of a suggestion for a sequel. There's no games that are bug free. And the other thing as well that's worth noting, a lot of people blame the bug testers when there's a buggy game. They say, oh god, how did the testers not find this? It's pretty much a guarantee the testers will have found it. Okay, but remember that the release dates are set by the marketing team, who don't understand game dev time schedules and things like that, and so they say, well, it's got to come out on time, so we're not going to fix that, you know. And the closer you get to the end of the project, the less likelihood there is that minor bugs are going to be fixed. Because the other thing as well is that sometimes when you fix a bug, it causes other bugs, or it reopens old bugs that you thought had gone away, and sometimes even a minor change can cause like big knock-on effects. That's why towards the end of a project, if you've got no Class 1s and you've got no Class 2s, it's probably not worth trying to fix all of those Class 3s, because you run the risk of breaking something else. So yeah, that's it. I mean, it's not so much of a big deal these days because, like, you know, with the internet, we can issue patches and things like that. Back in the old days, when it was a case of you get it on a CD and that's the game you get, it was obviously more of an issue. But yeah, bugs. Cool. Types of testing: iterative and final terminal testing. You don't need to know this in as much detail as you would do if you were doing A-level. Iterative testing, that's basically testing as you go along. Yeah, you implement a certain part of the program, you test that part of the program. Does it work? Yeah, it does. Cool. Now I can add the next part of the program, okay? And I can test that part of the program, and then I can test it all together, you know? So final terminal testing, that's where, like, you've got a finished product and you're testing the whole thing. Okay, so in iterative testing, this is where you're testing small parts of the program as you go along. Yeah, and then final testing, that's where it's like, right, it's done, let's go through and we'll have this massive list of things that need testing and we've got to test everything that's in there. Okay. How to identify syntax and logic errors. Syntax errors are usually easy to spot because they stop your program from working. You get a traceback that says, oh, there's a type error on line 5, you know, and so you can go to that line. Okay, reading the tracebacks is the way to fix your programs. It's something that students seem incapable of doing. Sir, this isn't working, okay? What line's the error on? I don't know. What line does it say the error's on? Line 5. So what line's the error on? I don't know. Right, you can't be helped. You know, read your tracebacks. Tracebacks are helpful as hell. You know, they help you out. But there's also tools in your IDE like the debugger, okay? The IDE is loaded with these cool tools, and you probably haven't been shown any of those. So I will have some lessons where we look at those. Okay, so just remember the debugger. What the debugger does is it allows you to step through your code line by line to find out where the errors might occur. Okay, so yeah, logic errors are more difficult to spot. That's because your program will work fine. Your program will work fine, but the output you get will be different to what you expect. Okay, logic errors are the cause of, like, the majority of video game bugs and stuff like that, because there's a lot of number processing going on, and if it's the wrong kind of processing, then you get all sorts of problems. There was a bug in Colin McRae Rally 3 where there was one level where the sun, like, gradually set as you drove around the course, and it looked really, really nice. But if you turn the car around and start going backwards, the sun rises again because they tied that functionality into, like, how far along the course you were. Is that a logic error? Perhaps. You know, it's not a massive thing. It's probably by design, to be honest, because it's like sometimes you reach the point where you're like, how are we going to do this? We could kind of cheat. No one will notice, you know. That's usually what happens. So yeah, spotting logic errors. The way to spot logic errors is you test the outputs of your program with known outputs for set inputs. Okay, if your program takes each number that's fed into it and multiplies it by 5, okay, you'll start off with your list of numbers 1, 2, 3, 4, 5. Okay, and what you're expecting out will be 5, 10, 15, 20, 25. Okay, and so you feed that in, and if your numbers match, you know that it works. If your numbers do not match, you know there's a logic error in there. Okay, so the way that you find logic errors, you feed in inputs that give you known outputs, and then you read those outputs. Another way of finding logic errors is using debug output. So you have print lines. So you can have, like, when you enter a function, you would have a debug printer which would print out the line, like, entry point for this function. Okay, it allows you to trace the flow of your program, because the other way of doing it is printing out your program and tracing it by hand. And that's the sort of questions that might come up in the exam. They'll give you an algorithm and they'll say trace the output of this program. So you sort of, like, note what the different values of each variable are as you go along. You know, and then selecting and using suitable test data. There's 3 types of test data. There's valid input, which is input that is supposed to work. There's invalid input, which is input which is not supposed to work. And then there's borderline input, which is sort of like input which is valid, but it's right on the very edge. So if you've got a system which says you can input any number from 0 to 100, 50 would be valid input, -5 would be invalid input, 150 would be invalid input, 0 would be borderline input, because that's right on the edge of what's allowed, and 100 would be borderline input as well. Okay. Cool. And then there's data representation. We've done loads of stuff on binary, and I've covered all of that stuff about how to represent images and sound. Compression, I haven't covered specifically, but you can kind of fluff your way through that. There's 2 types of compression, lossy and lossless. Lossy compression is compression that loses some of the original source data. Lossless compression is compression that doesn't lose any of the original source data. Obviously, the benefits of lossy compression are that you can compress things way more than lossless, but obviously you lose parts of the data. JPEG is an example of lossy compression. And if you do JPEG lossy compression comparison, you'll find tons of images that will show you some examples here. It's probably difficult to see on the stream here. If I zoom in, you might be able to. So this the top one that's like fairly high quality, and as we go along, it gets you can see the image are getting blockier and blockier. But this first one is 63K. The last one is 6K. So it's been reduced by a factor of 10 in terms of size, but we have lost that information. Lossless compression, as is used in things like PNG files or FLAC audio, you still maintain the fullest quality when it's compressed, but the downside is you can't compress it as much. Simples. The only other thing here is this translators and facilities of languages, including low-level languages. So a high-level language is something like Python or C++, stuff like that. A low-level language is something like assembly language. So if you're not familiar with assembly language, it's things that look like this. Stuff like that. That's like assembly language. It's difficult to comprehend, and it's not as human readable as a high-level language, you know. Examples of lossy and lossless compression. I've just seen your message there. Lossy compression: JPEG, MP3, MP4, MPEG video. Lossless compression: PNG, FLAC audio. Lossless video compression, I'm not sure, but you can find tons of examples online. So anyway, yeah, assembly language, it's closer to what the computer understands. The computer still doesn't directly understand it, but it requires less conversion before the computer can use it. In fact, you can, in theory, write assembly language just by using raw binary, but you'd have to be some kind of crazy wizard to do that. High-level language like Python or C++. I should state as well, this assembly language that I've typed in is totally made up. It doesn't correspond to any exact processor. The other thing as well with assembly language is, generally speaking, they will be written for a specific type of processor. Like x86 programming language is written for like the Intel like x86 series of chips. You've got 68,000 assembly language, which was developed for the Motorola 68,000, and so on and so forth. So what else? The difference between a compiler and an interpreter. An interpreted language is one like Python, where it reads the code through line by line, executing it as it goes, and it will execute your program up to the point where it creates an error, and then it will crash. Whereas a compiled language has to convert the entire thing into object code before linking it into an executable, and if there's any errors in your program, it will not compile. You will not be able to run it while there's errors in your program. Purpose of translators, obviously, to take the language that we write and convert it into the binary codes that the computer understands. That's what it's for. The characteristics of an assembler, a compiler, and an interpreter. Well, I've sort of just gone over that. Common tools and facilities available in an integrated development environment. You know PyCharm, you've used PyCharm. Editors, that allows you to edit the code. Error diagnostics, that's when you get your tracebacks and it tells you what line number the program error's on. Runtime environment, this is how many games have you had where it said, oh, you need to install the VC++ redist.exe. That's the runtime environment. If you've got Java as well, when you create a Java program, it assembles it into bytecode, and then it runs on the runtime environment, which has to be installed on the machine that's running it. Assemblers, yeah, things like the little man computer. An assembler is something that takes assembly language, converts it into binary, and then runs it. Okay, so that's assembly language. Low to high lang or high to low lang. Yeah, I mean, generally speaking, if you're writing something in a low-level programming language, it will get converted to binary code and then run. If you're writing something in a high-level programming language, you don't convert it to a low-level language. It just gets converted straight to object code. Okay, that's pretty much it. Da-na-na-na. And that's pretty. I mean, the thing with paper 2 is it's less about like remembering stuff and it's more about applying skills. That's why the project, although it doesn't count for anything specifically towards your grade, the project is actually really, really useful because it helps you develop the skills. What would you call code made for video games, as in code that the gamer puts into a game like Duskers to control it? Well, it depends. It depends how it's written. If it's written in a scripting language like Python or Lua or something like that, that will be high level, and it will be high level, and it will be interpreted. It'll be interpreted by the game in some way. But it's different for every game. So yeah, as I was saying, paper 2, it's less about your ability to remember and regurgitate facts. It's more about your ability to apply the skills that you have to any given question. So you are probably not going to do as well in this mock as you did in paper 1. Although, having said that, I haven't actually marked your paper 1 yet, so you might have done terrible. I don't know. But regardless, I want you to have a go, give it your best shot, try and answer every single question. Okay, if there's a question you don't understand, have a guess, give it your best shot, right? Don't leave any questions blank. If you leave a question blank, I'll be disappointed. Okay, and I will not buy you any fruit for Christmas. That was a movie reference. If you get that movie reference, you get a house point. So that is about it. Don't stress too much if you completely flap this one. We're going to have like 20 hours or more of working through the project, and by the end of that you will have so many skills that will relate directly to paper 2. You will feel a whole lot better for you. What's that thing? What thing on my table? What, this? No, you can't even see that. What? This? It's a pile of books. Is that what you're talking about? I've got a pile of books on my table. I've got The Road by Jack Kerouac. It's an amazing book which you should read. I've got what's this? Armageddon's Children by Terry Brooks. If you like fantasy, then give that a read. I've got this incredible Great Space Battles which is an amazing book from my childhood. Also, The Canon by William Sterling. I've got a couple of notepads, and what else have I got here? I've got a copy of Planet Hulk, Complete Planet Hulk, and I've got the Stargazing Journal for me to track and record my astronomical observations. Oh, and there's this one as well, right here, 100 Things to See in the Night Sky. So there you go. Got any Ray Bradbury? I've got a copy of Something Wicked This Way Comes, which is upstairs somewhere. I've also got a copy of Fahrenheit 451, but they're not on my table here. They're up on the bookshelf upstairs in my library. So there, you know. That's that. Any last minute questions before I disconnect and let you get back to whatever revision you are doing? Nah. I'll tell you what, just before I go, on the subject of Ray Bradbury, oh, did you hear that? That was a video. How do we subtract binary? You don't need to know how to subtract binary. You only need to know how to add binary. As far as I'm aware, binary subtraction is A-level stuff. Let's see, what does it say here? How to convert positive denary whole numbers into 8-bit binary and vice versa. How to add two binary integers and explain overflow errors. How to convert denary whole numbers into 2-digit hexadecimal numbers and vice versa. How to convert from binary to hexadecimal equivalents and vice versa. And check digits. You do not need to know how to subtract binary. But if you want to know, you need to know about 2's complement. And I ain't got time to explain 2's complement to you. The quick version is this: if I have this number, let's say 00110101, and I want to add, I want to subtract 00010101. What I have to do is first convert this number into negative, and the way that I do that is by 2's complement in it. So I flip all the bits 1 1 1 0 1 0 1 and then add 1, so I end up with that. So that's my new number, and then I just add them together, so I end up with what have I got? 1 plus 1 is 0 and carry the 1. 1 plus 1 is 0 and carry the 1. 1 plus 1 is 0 and carry the 1. 1 plus 1 is 0 and carry the 1. 1 plus 1 is 0 and carry the 1. See where this is going. 1 plus 1 plus 1 is 1 and carry the 1. And 0 plus 1 is 0 and carry the 1. And then we end up with 0. And there we go. There we go. We've done it. Hex to binary and vice versa. Dead easy. Right. I am not going through all of this stuff now because we haven't got time. Right. I will do a quick hex to binary. Let's say I've got this hex number for F. Okay. This first column tells us the number of 16s in there. The second one tells us the number of 1s in there. Okay, so all you do is take the first digit and multiply it by 16. 16 times 4 is 64. Okay, and 1 times F, well, F is 15, so that's 64 plus 15. You add them together, and you end up with 79. That's it. Okay, so you take the first digit, you multiply it by 16. You take the second digit and you just add it on. That's how you do it. converted the text to Highball Cairo. What text? I don't know what you mean there. Cool. That's the end of that. Right, it is now 9:15, which gives you enough time to go and do something awesome, and it gives me enough time to cry into my shoes and remember that life is the pain that I endure between disappointments. Best of luck. I don't know if your exam's in the morning or the afternoon. Come and find me to let me know how you get on. Either way, yeah, there it is. That's it. Obviously, this is going to remain up. So when it gets closer to the real exam, you'll still, I'll be doing some more live streams closer to the time anyway. But you'll still be able to like revisit this to help you out for your revision. Okay. Thank you, everybody, and I will see you tomorrow. Oh, yeah, see you tomorrow. Ah!